Okay, so let's get started. So I made a huge revise on the lecture notes, so you can take a look at the updated one in e-learning. So I just keep updating, so you should always look at the updated note and post it homework 3. Homework 3 is way easier than the homework 1, but the homework 3 is a bit more difficult. Anyway, so let's start. So last time, so we talked about the OPE, and then we focus on the stress energy tensor for the stress energy tensor for the free scalar theory. And then at the end of the day, so we just derive the following quantity 1/12 C minus W squared force plus 2 TW C minus W squared plus ratio TW. So this is a singular part. So for singular part, I just use sim or tilde for OPE, and this is 2. Due to the presence of this term, T of Z, stress energy tensor, energy momentum tensor is not primary. Yeah, so that's what we have concluded last time. Okay, so that's what we have, where we ended last time. And then we'll move on to analyze the basic 2D CFT. So even though here presence of this 1 over z to the 4th term, it's not primary, these 2 indeed encode the compound dimension. So therefore, Tz is the compound dimension is 2, 0. Of course, if we consider the anti-homomorphic part, the compound dimension is 0. This is quite natural that the, of course, T mu nu, dx mu. So the stress energy tensor is like this way, and then if you can easily see this is spin 2. Spin 2. So therefore, the compound dimension is 2 dimension. And then, so even though, and also, so this term mentioned that the stress energy tensor is not the primary, but this encodes very important information, so-called central charge, and I'm going to explain. Central charge, usually called C. Okay, so usually in 2D compound field theory, CFT, stress energy tensor, takes the following form: C over 2 Z minus W square. If it is the non-chiral theory, non-chiral is homomorphic and anti-homomorphic sector is the same. Plus partial TW. So this is the usual form for the OPE of stress energy tensor in any 2D CFT. Maybe it's better to replace it in C left. Or if chiral CFT, non-chiral CFT is just same as C over 2. Non-chiral means CL is equal to CR. Left and right moving, left and the right moving central charge is same. So in other words, holomorphic or anti-homomorphic are the same. But if you consider general CFT, left moving and right moving sector can be different. So therefore, it's better to replace CL, but in this lecture, most of the case, we focus on the non-chiral. C left is equal to C right. Okay, so that's the central charge, and the central charge encodes most. This is one of the most important information to the CFT. Then. So to express why this is the most important quantity, we need to use the conformal transformation. So if you use conformal transformation to move from the C to cylinder, not being plane, so what we have learned is C star goes to the cylinder. So that so the map is Z to the E to the minus IW, where W is equal to sigma plus IT. So what I meant is the cylinder. So C star is just the origin removed inside a C, and then the cylinder is something like this way. And this direction is sigma, this direction T. And now we use the Euclidean signature. That's the Z plane, and this is W coordinate, which is sigma plus IT. Then you can just use the conformal transformation to show that, so we would like to move from one to the other by conformal transformation. And we would like to know how this stress energy tensor is transformed under conformal transformation. To do that, so we can use the conformal or Takahashi identity. Namely, you just plug in the TZ in the conformal Takahashi identity, which is 2 pi I, CW. DC, E of Z, TC, and TW. And we already did this, the OPE of the to this stress energy tensor, energy momentum tensor. What we can obtain is 2 pi I, and just plug in the stress energy tensor here, which is C over 2, C minus W to the force, plus, of course, 2 TW C minus W squared. Actually, this is not, it just gives plus partial TW Z minus W. Okay, so you just plug in and do the usual contour integral. Then what we obtain is that the sorry, so it should be depends on C, sorry. Okay, anyway, so EW partial TW, and then this term really come from here, and I think I should put EZ. Sorry, I omitted many things. So DC, and here I multiply E of C, multiply. Then the first term will give you this one, and the second term will give you, and this term will give you C over 12 E 3 times W. Sorry. Okay, so the first term, then last time we will give you the first time, the second time we give you this one. Because this is one over z squared, you need to do the first derivative, and this is 1 over 4 z to the fourth will give you third derivative up to some number. So this is 3 factorial times 2 will give you 12. And this is the infinitesimal transformation under the compound transformation. Infinitesimal transformation of the stress energy tensor of the under the compound transformation. So yeah, this is the infinitesimal transformation. Have a finite transformation. This one I just give you the answer. So I think I should use T Taylor of W. So under the transformation, T goes to this homophilic transformation. So this is compound transformation. T Taylor new stress energy tensor. I call it T Taylor. It's just a usual factors that appear for transformation, compound transformation. But since this is not the primary field, it becomes the cost of that. So without this term, so it just becomes the just compound transformation. Primary transformation primary field. Since the stress energy tensor is not the primary field, you have some cost. That is actually responsible this term and this term. So, and this S is called Schwarzschild derivative, which appear in the also homework. So this is defined as W prime square and W prime, W3 prime minus 3 over 2 W prime square, and this is called Schwarzschild derivative. So this is finite transformation. So if you take the infinitesimal version of this one, you get this one. This is homework. Okay. And so the prime means really dz, dn, w, dzn is equal to wn. The prime means the derivative is restricted. So now we know how the stress energy tensor is transformed under the compound transformation. We would like to perform what's going to happen when we transform from plane to the cylinder. Okay, that's what we want to do. Any questions so far? So we can do. So we can just plug this compound transformation into here, and what we obtain is the cylinder of W. Is that you can easily see derivative with respect to z of this quantity is you just get the minus 2 t of z. But however, we have to plug this one into Schwarzschild derivative. Okay. Then actually you can easily take log. So W is equal to what? Log z times I, right? Log z times I, and you take z derivative twice, you get the minus z to the minus 2, and then just do the honest calculation. Just plug this one into there and compute the Schwarzschild derivative, and what you obtain is c over 20. Okay. So this will give you so-called the ground state energy. So this will give you, so the cost of this, the transformation is, if you map to the cylinder, what you obtain is that the ground state energy or vacuum energy for this 2D CFT. So this will give you the ground state energy or cosmic energy, energy of ground state up to the CFT. So I will explain why you get this. So energy just is Hamiltonian, the eigenvalue of Hamiltonian. So Hamiltonian can be obtained from stress energy density. So we just do this, just Hamilton formulation of this system, and you see why this will give you the cosmic energy or ground state. For instance, Hamiltonian is just the sigma dtt. So sigma is this direction, the spatial direction, and take the dtt is the energy part of the this is called energy momentum tensor. So therefore it encodes the information energy and momentum, and dtt is the energy part, and then take this average of a spatial direction, you get the Hamiltonian. And this can be understood as the minus the sigma. You just do the honest calculation for then plug this one into here. So what you would obtain is that this one will give you that the E is equal to minus C plus C left or C right. In the lecture note, I just write on C bar, C plus C, CL, CR, and 24. Okay. In other words, this quantity can be just do this Fourier expansion for minus is equal to minus n is equal to z, and I will explain what's. So you already did the exercise homework. You obtain from the stress energy tensor to some Fourier mode Ln, so that's called Virasoro generator, and minus c over 24 delta n0 e to the I n w. So this is the other some transformation for stress energy tensor on cylinder. So therefore, what you can obtain, you just do the Fourier integral over over this coordinate w, and you just if you do the Fourier integral on sigma, only constant mode will appear. Okay, I think yeah, constant mode will appear. So therefore, if L0 is indeed energy part, and the C is indeed will give you the cosmic energy. So that's another way to obtain this relation. So therefore, central charge encode the information about the cosmic energy of the 2D CFT, and in particular, so free scalar theory. Free scalar theory, we obtain Tz, Tw is equal to 1/2 z minus w squared plus dot dot dot. So therefore, the central charge for free scalar theory is equal to 1. So therefore, energy density or cosmic energy for free scalar, free boson is equal to e to the minus 112. So again, what we have shown is that the cosmic energy of free boson is negative. Okay. So and the tachyon, last time we saw is that what we have seen is that the first lecture, I think, as far as I remember, the cosmic energy or state, the tachyon state, the ground state is tachyonic, and then so the energy is indeed equal to energy is equal to d minus 2 divided by 24 minus. So in d dimension, the energy is equal to 24. Let's see. So then minus 24, and this is equal to this is energy tachyonic state for the up to the sorry, I think normalize. I forgot to go over alpha prime. So normalize 4 over alpha prime. And then each, so here, the free scalar, what we have done is T of Z is equal to minus alpha prime, partial x of Z. And I forget about all the, so usually you need to include all the mu. All the mu. If you sum over mu, you get the d times this number. So therefore, so each dimension will give you minus 1 over 12, and at the end of the day, if you sum up both, let's see, left and right moving sector, you will get this one. I don't know how to get it. D minus 2. So here we take the light cone gauge. D minus 2 really come from the, if you forget about the light cone direction, and so D minus 2 come from here. And what is the normalization? Why you get 24 instead of 12? Where is that? Let's see. That I don't remember. I should have known. Let's see. Oh, what I'm doing? So sorry. Yeah, I just omit the detail. So E is equal to, what is that? Oh yeah. Here 24, and C left and C right is 1/2 and 1/2, and you get yeah. Why don't I get right 1 over 12? It should be. Sorry, it should be. Yeah, C left and C right give you 1/2, 1/2. It should be 24. Sorry, there's a typo in the lecture note. Okay. So therefore each dimension you get the minus 1 over 24, and then up to normalization 4 over alpha prime. I think I just omit a normalization of 4 over alpha prime, and if you take right cone gauge, you get the d minus 2 direction you need to consider for mu. Okay. So therefore each dimension except this light cone direction, you get the minus 1 over 24 direction, and at the end of the day you get the energy for tachyonic energy for bosonic strings. Okay, so that's how we obtain the ground energy for ground state of string theory. Okay. Any questions so far? So then, some of you have already did the computation for computation for Irrational algebra from OP of stress energy tensor. So from this OPE, so this OPE is very important, very fundamental in 2D CFT. And then we can do the model expansion. So since the stress energy tensor in this flat plane, we can do the Fourier model expansion, which is this -2 really come from the conformal dimension of the stress energy density. For instance, J of Z is up to some number, up to some constant is partial x of Z. So that we have derived the U1 current. This is our like laser current for the translation. So this can be just expanded in Jn minus n minus 1. So this has conformal dimension 1. That's we already showed last time from the TC. So we just compute this one. Okay. So this is we already derived last time, and its conformal dimension is 1. So always this Fourier mode, you need to shift the conformal dimension, and then to get the algebra for this Fourier mode as a it's a quantum field theory. So it's an operator, Ln or Jn operator. And so therefore, to get the computation relation for Ln, we just need to do the contour integral of this the OBE. And this is most famous the most important relation into the CFT. You will get so Lm. This is already did it in homework, and if you want to learn 2D CFT, you have to do always. I mean, this one it's really fundamental relation minus dw. It's called Virasoro algebra. And then Z, it's just a Fourier mode expansion. And TC and dw. So to extract, you have to extract Lm, you have to multiply d to n plus 1, and then just do the contour integral. And then to get the Ln, you just multiply w to the n plus 1 and do the Fourier contour integral. Okay. Then to get the commutation ratio, you swap z and w. That's it. And then yeah. First, you need to do the how to say z. So if you do the w, there's the oh my goodness. My hand drawing is horrible. So z integral and w take here. Okay. I don't know which one we should take. This one is here, and another contour integral here. You get a bit. You just take smaller than w here, and z integral is here. Integral. So this minus this one is equal to just the w is here, and the contour integral is here, and z plane. Okay. So if you do the integral over around the w, and then after that you get the w contour integral. That's what you need to do. Okay, and then so you did a homework. At the end of the day, you get the most important relation into the CFT. So in the homework, you just derive Ln, this is equal to n minus n, Ln plus n plus c over 12 n minus n squared. So this is Virasoro algebra. So this is the infinite dimensional algebra that governs the 2D CFT. So since you have an infinite dimensional symmetry, so therefore 2D CFTs, you can just get an exact result often. Do you know Virasoro is, which country Virasoro is from? No. He's Argentinian. I don't know, actually it's 1960, late 1960 you get this, he got this one. Or maybe around 1970, I already forgot. You can search in Wikipedia. So in some sense, so in homework you did I don't have the, let's see, exact relation for so this is extension for the with algebra. This is what you have done in the homework, and I just want to know about how they write the generator with algebra. Yeah. So ln. So this is the ln is equal to minus t to the n plus 1. So this is the if you define the generator like this way, this satisfies without this term. So this is what you have done in homework. So this is called with algebra. With algebra. So Virasoro algebra is called central extension. This is called central extension. So C is actually central element which commute all generator. It's called central extension, and this central extension is very important. Any questions so far? So of course you plug this relation into here and do the contour integral. That's what you need to do. So that's what you some of that question. Good question.
There is similarity in the TZ and TW. There will be Z minus, there will be similarity at Z equals the omega. So the counter integral, the first counter integral must contain no singularity. So the first omega should be inside of the Z.
So here, let's see. Good question. So here, so what John Hao mentioned is that here, where should I write? Time ordering is that if you map this plane into cylinder, the first one is something like this one. So this is t direction, and there is the point which corresponds to W. The first one is the after the point W, and the second integral is the before W. So that's what he mentioned. And then so what you mean is that so when you do to get this one, so ZTZ and TW, and the time here is, how to say? Time here is, how to say, future than this one. And when you do this one, you need to do the TW whatever. When you do this one, so that you have to swap the ordering of time. That's what you mean. Is it what you mean? What is the question? Yeah. Yeah. Okay, let's see. Uh-huh. So you mean, so here, like this way? You mean? Yeah. Sorry, I don't quite understand what your question is. Maybe I can answer after, during the middle break. Yeah, I think here definitely we use time ordering. Yeah. Any other questions? Yeah. Here definitely use time ordering. Yeah. Elon, I think it's the best place to consult is Blumenhagen. I can put the it's recorded, right? So it's better not to say. Anyway, so you go to the library, go to library, and then look at the Blumenhagen's book. Any other questions? Okay, so we got the most important algebra from into the CFD. From here, I'm not going to explain anything about the affine Katsumuri, affine Lie algebra, and so on. So from here, there are lots of how to say. Lots of generalization for this infinite dimensional algebra, so-called Katsumuri, the affine Lie algebra, Katsumuri algebra, which usually you have the Lie algebra G, which will give you whatever SL2. For instance, SL2 case, you have Jx, Jy is equal Ji, J is epsilon ijk. So this is SL2 Lie algebra. It's finite dimensional Lie algebra, but you can just add some mode expansion like m and n, and you again have some m plus n, and you have some coefficient, and you have central extension so on. That's called the affine Lie algebra that governs the symmetry of so-called Zimina-Wicked model, which is also famous, exactly solvable to the CFD, and so on. So there is lots of generalization of this infinite dimensional Lie algebra, but I'm not going to explain. So due to this symmetry, one can just obtain the exact result into the CFD. Okay, so we obtained the Virasoro algebra, and then let me move on. So now, so here, oh, I already erased. Here we map, so you can barely like a manage to see this. I just map a plane to cylinder, and there is a state operator correspondence. So that the okay, let me. So state operator correspondence into the CFD. So the state is some map to the cylinder as I mentioned last time. So there is a state you can associate each state on a spatial slice on a cylinder can be mapped to the circle in the plane, and if you do a conformal transformation, just scaling transformation on the radial direction, you just map to the origin, and that will create some operator that's called state operator correspondence. And now, so in the bosonic string, we already saw that the ground state is tachyon state is labeled by like this way, which when you act as momentum tensor, you get this one. The question is, what is the corresponding operator? If you have a state, there is a corresponding operator. And that can be easily guessed. So guess, I mean, if you do 0k and it's just a 0, 0, and do the 0k, it's just a, how to say, the translation with momentum k. And that is always created by, this translation is always created by this operator. So therefore, in the target space. So in string theory, so we just consider, you can easily guess, the Riemann surface mapped to, at this moment, we just consider d-dimensional Minkowski space, or R1, D space, or D-1 space. And so to get this state, so you just do the translation with momentum k. So that translation is always generated by this operator, as you know, in the whatever classical mechanics. So therefore, you just replace this x is a coordinate of the target space, replaced by the bosonic operator x and 0, 0. And now it's quantum field theory, it's an operator. So we have to specify the ordering, and we just use normal order. So this is a natural guess for the corresponding operator for the tachyonic states by using state operator correspondence into the CFD. And we can just convince yourself by using OPE. By using OPE, so by using OPE, so P mu is corresponding to the contour integral of 2 pi I of partial x, partial xz, up to some sign, up to some number. I think alpha prime, 2 over alpha prime or something. And do you see this one? This momentum operator corresponds to this one. Do you see? Do you see the correspondence between these two? So as I mentioned, the current is the Nether current is the symmetry that is correspond to translation. Okay? And translation is of course this e to the ikx, right? And if you do the mode expansion, this is indeed Jn is indeed equal to alpha n. Alpha n in the mode expansion. And if you look at zero mode, this zero mode is P mu, as I mentioned. Zero, this is zero mode. Alpha 0 corresponds to P. Okay. So therefore, if you do the contour integral here, you get a P here. Okay. So therefore, and if you do the OPE of so I should write down x mu OPE with this quantity e to the I kx 0. Then, I mean, did you do, so this is one of the homework or no? It's TT. I already forgot the first homework. So you get the I alpha prime k mu to z minus, and then you have an e to the I k x 0. And then, as you can easily imagine from here, the coefficient should be, so the correct, if you do the careful computation, coefficient should be this one, 2i. Then if you do the contour integral of this one, you get the p mu is equal to k mu. Okay? P mu equal to k mu. That is the same as this relation. Okay? So therefore, you can easily guess, and then just you can check by using OP. See, so therefore OP is very, very fundamental. Essentially, 2D CFD, what you first do is just do the calc of the OP and then do the contour integral. That's all thing you need to do to get the physical quantity. Okay, and then now, so next question is what is the massless states? So we have learned is that the massless state is just acting on the -1 alpha tilde nu -1 acting on this vacuum state. So this is massless state. If you take symmetrical part, you get a graviton. If you take anti-symmetrical part, you have a Cauchy-Lamont B field. If you take trace part, you get a dilaton scalar field. That's what we have learned in the first lecture. The question is, given the massless states, what is the corresponding operator? We can do a similar exercise. So what we want to understand is what is the corresponding mode. So alpha minus m should correspond to, instead of just without multiplying anything, you just multiply something. Okay? To extract information about, and somehow, but so now the mode, if you do the mode expansion, the normalization is a bit different from the zero mode. So zero mode, somehow you need to multiply square root of 2 over alpha prime or something. So the normalization is a bit different. You need to normalize like this way. So this is the correct normalization to extract the non-zero mode for the nether current. Okay? So therefore, we can do the similar exercise. So you just get them m is equal to -1 component. What is the corresponding state? And you can easily guess the fact that the so this is equal to, therefore the corresponding operator should be something like pi over 2 alpha prime 1 over m minus 1. So you just do the contour integral. The prime per short m is factorial x 0. And now we want to know what is the corresponding operator for m equal to 1. Okay? The m equal to 1 case, and then so therefore corresponding operator should be partial x mu, partial bar x mu, and then that acts on the vacuum state. So this is corresponding operator by state operator correspondence. Okay. So this vacuum corresponds to this operator, and the alpha minus 1 corresponds to this operator. So that's the state operator correspondence loss. And then to extract the mode, you just the graviton, you just take symmetric part. To get the B field, you get the anti-symmetric part, and you just take trace to get the field. So to do the operation, you just multiply some polarization vector. I mean, if you learn quantum field theory, you always have if you have a photon mu, you need to have the polarization vector. Okay, polarization vector. So likewise, even for cross string, you need to multiply some polarization vector to extract the mode. So to symmetric, anti-symmetric, and trace and so on. So this is polarization vector you usually multiply in such a way that as you can easily so this is 0. So it's just a light cone. So the K mu is here, and of course the mode has to be always transversal. So it's Xc mu should know about it. In other words, it's a representation of letter group, SOD minus 2. Okay. And then furthermore, we already knew that this is tachyonic state and this is massless state. Question is, can we get the same mass spectrum for this one by using 2D CFT? And that is the case. Of course, as I mentioned last, so here this compound dimension is related to spin and so on. Therefore, compound dimension has to do with the energy. So also here, as I mentioned, compound dimension will give you the vacuum energy, right? Therefore, this compound dimension, central charge corresponds to describe the energy of the vacuum, and also this central charge coming from the just taking the OPE of the stress energy tensor and so on. So therefore, this mass spectrum and so on should be able to extract from 2D CFT, operator 2D CFT. And that's what we are going to do. And as you can easily see, compound dimension should be the one we should look at. So, in fact, in the string amplitude, so when we consider the string amplitude, let's see. So you have a Riemann surface, a bunch of state you can consider. And as I mentioned last time, so this is incoming state and outgoing state. This is outgoing state, so it's a punctured Riemann surface. Should correspond to, by using state operator correspondence, it's the correspond to some vertex operator here. So this state, physical state corresponds to some vertex operator by using state operator correspondence. And this can be obtained by just doing the Feynman path integral. Schematically, it's just HAB. So this is a metric of Riemann surface, and then dx, and it's e to the minus string sigma mode action times vertex operator insertion. And this vertex operator is indeed can be written as dz square to h, and it's this operator. It's this operator, O, Z, and Z bar. So this is the essential form of vertex operator. And in order for this operator to be conform, so this amplitude, so this string amplitude should be enjoy all the symmetry of the string sigma model. So we already know this is diff invariant, diffeomorphism invariant, and also there wild symmetry and a Poincare invariance. In particular, to enjoy the wild symmetry, it has to be constant under scaling. So Z goes to, this is scaling transformation. We have a scaling transformation like this way, under this scaling transformation, we should obtain B has to be invariant under this while scaling. So this is because it's a scaling. So scaling of the coordinate that can be realized by using the scaling of the metric. Okay? Metric. If you scale the metric, I mean you can zoom into the region or zoom out. So that's what the while symmetry do. So while transformation does, and also this can be also understood as a diffeomorphism of the Riemann surface. It's just scaling is just diffeomorphism. So therefore, this vertex operator should be invariant under this transformation. We already knew that the operator is transformed under the scale transformation by just, we already know in 2D CFT, this dv bar is under scale transformation. You just have lambda to the minus h, lambda bar minus h bar, and the operator. Can I erase, or maybe I should write them somewhere else. So operator Z bar under scale transformation, we already know that we just come the scaling by conformal dimension. Operator Z bar. So this is how the operator into this CFT with conformal dimension H bar should transform. And we know that this measure is scaling lambda Z and lambda bar Z. So therefore, in order for this vertex operator to be invariant under the transformation, H and H bar has to be equal to 1, 1. Okay. Well, this minus 1 cancel with this lambda for this measure, and this minus 1 cancel with the transformation of this measure. So therefore, at the end of the day, this vertex operator is invariant under the scaling transformation. So somehow, and then so we know that this conformal dimension. So you guys did this exercise. That's why I give you an exercise. This conformal dimension is H bar. That's why I give you homework. This is alpha prime in square over 4. So this is conformal. So this conformal dimension can be obtained from what? How do you obtain the conformal dimension? Of the operator. Good. So if you do the operator of Z, and if Z is the primary field, always H O Z, Z minus. So this is the transformation rule for primary field. So always, if you take OP conformal dimension, can be read out from here. Therefore, computing the OP is very important to the CFT. Okay, so therefore, so this H bar has to be 1. So therefore, K squared has to be 4 over alpha prime. 4 by alpha prime, and then this is minus of m squared. Okay, m squared. So therefore, the energy for the tachyon is minus sine 4 by alpha prime. Okay, for each dimension x. Okay, each dimension x, and if you take the light cone gauge d minus 2. Bosonic mode will contribute. So d minus 2 times 4 times alpha prime times minus will give you tachyon energy. Likewise, you can do the same exercise for this state. The compound dimension is, here, as you already know, this is compound dimension 1, and this is compound dimension this one. So you just have compound dimension is 1 plus alpha prime k squared over 4, 1 plus alpha prime k squared over 4. So in order for this to be 1 plus 1, k squared has to be 0. Okay? So therefore, it should be massless. K squared is equal to minus m squared. And k squared is 0, so therefore, this state has to be massless. Okay, so therefore, at the end of the day, we get the correct operator and the correct mass for tachyon first excited states. Any questions so far? I think I made a mistake. Sorry. So tachyon state, the energy is 4 prime over alpha prime d minus 2, 24, right? And then we take d is equal to 26. This will give you minus 4 over alpha prime. And that corresponds to this one. Okay, sorry. I need to consider. And here x mu is everything, it should be mu. It's a mu and a mu. Oh, mu means the contraction with, k mu and x mu. Okay. Do you understand? So you have to consider all the dimensions. Okay. Oh, I think I use mu and nu here, so I think I should use some other k rho, x rho, k rho, x rho. Here everything's same. K rho, x rho. It's just contraction on the target space point. Any question? Okay. So this is the very, very crash course of 2D CFT. And then we will move on to the, we will continue to learn 2D CFT, but string perspective. Yeah, it should be. Because, usually, instead of considering usual just ordinary scaling, it should be diffeomorphism invariant. So one can consider usual transformation z goes to wz. So you can just consider usual diffeomorphism. It's a holomorphic. But in this case, this measure is transformed, so dw is transformed partial dc squared, right? And this should be cancelled with the transformation for primary. If this is not primary, then the extra factors show up. So therefore, it cannot cancel. So it should be primary. Any other questions? So now we'll move on to a little bit advanced topic in string theory. So the plan on this lecture is first do the bosonic string. And then next is include fermion. Include fermion. So now we already know 2D CFT is also bosonics. Free scale. We only learn free scalar. And then next we include both boson and fermion. And we'll see some symmetries which is called supersymmetry. And we will go to superstring. So the bosonic string, what we will consider is called how to deal with this path integral. How to deal with this path integral, and before that, we need to consider a bit more general string theory. So first, we try to generalize the bosonic strings. We first consider the Riemann surface is mapped to the just ordinary Minkowski space. But now, this lecture we replace this one. This is eta mu nu. So it's just a usual Minkowski space. Instead of this one, we just replace some manifold, d-dimensional manifold, and the general metric. So this is nonlinear Siegel model, and we will see some anomaly. So this is just free theory. But here you have more complicated theory. Once you map to some non-trivial manifold, you need to be careful about the quantum phenomena. And then that's called that is related to wild anomaly. That's what we are going to learn. And furthermore, what we are going to learn is how to perform this integral. So since we have a lot of gauge redundancy, diffeomorphism, wild symmetry, Poincare imbalance, and so on, so we need to fix a gauge to perform this path integral. And they have some of you have taken my QFT2 courses. To fix the gauge, we need to introduce so-called ghost. So for instance, when we learn the Yang-Mills, so there is a non-abelian gauge theory, quantum Yang-Mills theory. So to fix the gauge for this gauge symmetry, we need to introduce Popov ghost. And also by introducing Popov's ghost, we saw the so-called BRCT symmetry. That's what we have learned in what you have learned QFT2. If you take my course, or maybe some other people. So does Janet explain this one in particle physics? Last semester she taught.
Not last semester, but 3 years ago.
Huh?
She talked about it 3 years ago.
3 years ago. Okay. Okay. But last semester she also taught particle physics, right? Does anybody have taken? No. Oh, you have taken. Does she teach this one? No. Okay. Anyway, so I have already taught QFT2, and somehow all the lecture like order, so you can just take a look at it if you don't. And we need to do the same thing. To fix the gauge for these symmetry, diffeomorphism invariant, and so on, we need to introduce ghost field into the CFT and fix the gauge. And if you introduce the ghost, you see the BST symmetry. We do the same thing. And then if you do that, after that, we can just do this computation for this string amplitude. So that's the bosonic string part. That's the first part of the lecture. So. Yeah, so first we look at the wild anomaly, just considering the general target. And next, we will fix the gauge by introducing closed, and then BRC symmetry, and then we will compute string amplitude. That's called famous Venetian amplitude. And after that, we will introduce Fermat into the CFT. Actually, the goals is actually kind of Fermat field, but we just introduce usual physical Fermat field and consider supersymmetry. That's the outline of lecture. And once you introduce supersymmetry, after that we can see lots of more interesting stuff like a string duality and so on. That's more advanced topic. But till then, we will essentially do the 2D CFT. So let's consider wild anomaly. So even before, so far, even before taking this general background, we just consider only like a flat 2D CFT in flat background. So we just consider the plane, star, or cylinder. So far we just consider 2D CFT on only plane. And what if instead of just keep the target as it is? Target is a Minkowski space. It's a free theory. So let's keep, but consider the general Riemann surface and general metric HAB. So first, slightly generalization, not without going to stepping further. Stepping further, so let's slightly generalize the problem. So we consider instead of the plane, we just generalize the metric of the 2D Riemann surface as the more general, keeping target as a free theory or Minkowski space. So then, so-called, again, we can see so-called wild anomaly. Anomaly means since the action has a wild symmetry at the classical level, but at quantum level, it's broken. So that's what we're going to see. Once you replace flat Riemann surface to the general Riemann surface. So this is called wild anomaly. I don't know, today my condition is very good. Curved worksheet. So as I mentioned, so the wild symmetry, classically wild symmetry is, as I mentioned, so the HAB is mapped to e to the phi. It's just scaling of the metric. The scaling of metric leads to traceless condition at classically. And in the quantum mechanically, this is not the case. And then this is anomaly means that this is no longer the case. This is anomalous. Once it replies, the HAB is the instead of the just the ordinary flat space. However, so we have so-called even at the quantum level, we want to have worldsheet diffeomorphism invariant, and also at the flat space, it should be 0. So we already know the conform field theory. Conform field theory, we just have a TA equals 0, even quantum level for flat worldsheet. We need it. Okay, so flat TAA equal to 0 for flat worldsheet. And also we need a so this TAA has a conform dimension or mass dimension. TAA has mass dimension. Mass dimension 2. So that can be easily see that the T mu nu is dx mu and dx nu. Okay, this is the conformal dimension 2, so that corresponds to the mass dimension 2. So therefore, these three quantity easily tell you that this TAA has to be proportional to Ricci scalar of two-dimensional worldsheet. Even if so this one anomaly, if there is an anomaly, these three facts should restrict the form of the anomaly. So as you can see, so this Ricci tensor is invariant under diffeomorphism, and also once you take flat limit, flat means Ricci tensor is 0. Okay, so therefore it becomes 0. TAA becomes 0, and also as you know, the Ricci tensor in 2 dimensions is mass dimension 2. Okay, so therefore it should be proportional to R2. Okay? That's physicists usually do. It's a natural guess. Physicists usually do the guess and try to check this guess is correct. I mean, that's usual thing usually do in physics. If you try to construct Lagrangian, people just guess. Given the symmetry of the system, you just guess all possible Lagrangian terms and just sum them up by using by just multiplying coupling constant. That's physicists try to construct a Lagrangian and check this is correct. That's usually physicists do. And so it's just some constant. I call it A. This A is not the same as this A, so let me call it BB, maybe. It's just contraction of the tensor, and A is some constant. Lecture note, I use same A, but they are different, so be careful. And we would like to determine this A by using, conformal transformation. So that's what we're going to do. So So the metric HAV is something like H11, H12, H21, H22. So this is two-dimensional metric. It's very simple. And then it's symmetric. It's symmetric on the swapping V. So this element should be equal to this element. That's what we have learned in the differential geometry course. What she has learned differential geometry course yesterday. So we have 3 physical degrees of freedom, but now we have worldsheet diffeel, so we can kill one of them. By using worldsheet diffeomorphism, we can kill one of them. So we'd like to kill the 1 degrees of freedom by worldsheet diffeel. So I just want to kill this off-diagonal element. Therefore, by using worldsheet diffeel, the metric can be written equally. So you can just have only diagonal element, which is just a one scaling of it's called conformally flat metric. So we like to take this one, and then if you take this is conformally flat. It's called conformally flat. So then, if you take this one, the curvature is written as just a usual way to compute BG tensor for rich tensor and Christoffel symbol. So other Christoffel symbol, like for instance ZC bar, these are all zero. Other Christoffel symbol are zero. Other connection or Christoffel symbol connection are zero. So this can be just computed by using usual standard method of the GR. So therefore, what we want to show is that we can just have this trace of the stress energy momentum tensor is just -2 times some constant delta bar omega. Oh, I'm sorry. I think I made a mistake. I think I shouldn't tell. I mean, sorry. So T Z bar is GZZ bar and then T Z bar, and this GZZ bar it corresponds to this one. So you have e to the 2 omega, and 1/2 should be here, and times TZZ bar, and sorry. So 1/2, so the 1/2 TAA. So TZZ is equal to, sorry, I think I made us, let's see, what I'm doing here. Am I doing correct thing? I hope I'm doing correct thing. So I think this is correct. I'm not careful of constant. How do you get this one? Yeah. What am I doing here? Sorry. So then this is equal to, so let's assume this is correct, and 1/4 e to the 2 omega, and you just plug this one into here, and this is -2a partial a omega, and then this is equal to, is plug this metric into here, what you will get is -2a delta bar omega. So that's what you get. I think I made maybe some are wrong, and it's a good time to stop take a rest. So during the break, I will just fix this problem, and let's take a break. And I will determine. So what we are going to do is to determine A by using conformal symmetry. Okay, let's take a break. 10 minutes break. What are you doing here? Oh, yeah. So if you've done homework, just submit. Oh yeah. And if you submit the homework, you can take here from here. Okay, so again, you can have some sweet during the break. You can just open, and then you can open and just distribute to everybody. So So this is very famous souvenir in Japan. I never tasted it. I want to try one.
这个是有跟那个是它这个光跟它流水有关系，非常非常巧，就是这个然后它这个相当于是那个。就是实际上只要总共有把这样对起来就这个我就单用这个其实也是个错误。我怎么可能直接
So, not every week I'm gonna bring sweet, but I occasionally bring sweet in this class to attract more audience, so you can have it for free seat. So let me. So it's space energy has a symmetry. T mu nu is equal to T mu mu. Then it's okay. This is okay. So I think it's better to right now correct down. Okay. Shall we start? If you want to, you can take a bit more. You can eat while you're listening my lecture. Phew. Okay, so let's start. So this is correct relation. So TAA is the trace is TZZ, TZ bar, Z bar. And this can be, so the only non-trivial element is, so the question is, so before going that, so question is you can just get rid of by wild diffeomorphism, but the question is why H11 can be equal to H22. But even if they are different, you can have another redundant, another diffeomorphism to at least fix the scaling. You can just the scaling to match dxx, d11 component, d2 x11 component, x22 component. And also, trace is ZZ and Z bar. And then non-trivial element of GAA is, of course, in complex coordinate only of diagonal component 0, 0. And this is G, Z bar, and Z, whatever. Non-trivial component here. Okay, it depends on how you take. And they should be the same, but due to symmetry. So the TZZ is equal to Z bar Z times this quantity. What I'm doing here? Yeah, and Z bar Z times TZZ bar. Therefore, 2 times. So this one is equal to 2 times E omega minus 2 minus E to the 2 minus omega 2 times E to the minus 2 omega 0, 0. Okay, so therefore dz bar z component is this one, and you have a 2 copy of tzz bar, and you get this one. And applying to this one, you get this one. Okay, you just take bring 4 times e to the minus 2 omega to here. You have tzz bar is equal to this quantity. Okay, and then TAA is proportional to 2-dimensional Ricci scalar curvature, and 2-dimensional Ricci scalar curvature is this one. Therefore, plug that in, you get this one. Okay. Yeah. You get this one. Okay. So everything works. If you don't understand, you can just do the calculation by yourself. So now we want to see. So we obtain the TZZ bar. How about the other component of the energy momentum tensor? So energy momentum tensor, it can be obtained by just conservation rule or conservation energy momentum tensor. So this can be written as in the complex coordinate, 0 is delta z tcc. Now maybe I should write down AB and A. In complex coordinate, so this is the conservation of energy momentum tensor. And now, so we already know that this covariant derivative can be expressed by using this connection or Christoffel symbol. And then you should be fluent about this kind of computation. So using a matrix, so you just have a TC bar. Z, and then we have this one is just the above. The other component of the other component crystal pair symbol all 0. Okay, all other components. So when this nabla Z bar acts on this stress energy momentum tensor, all crystal pair symbol vanish. So therefore, only have a normal derivative, anti-homomorphic derivative. However, this one you have to be careful because here you have partial Z minus 2 omega 4t Z bar Z. So here this component really come from this guy. So this guy, and so you need to take into account it's this crystal symbol. And now we plug into this quantity into here. What you obtain is that the TZZ plus and this quantity minus 2A. Okay. Now we just how to say manipulate this. This one acts on here, but now we, as you can easily see, the first one you have two derivatives homomorphic and one derivative anti-homomorphic, and this one you have two same quantity, but one is have anti-homomorphic. So therefore, this can be simplified to the following form. So this one can be simplified TZZ minus 2A So now, so if you act this anti-homomorphic derivative on here, you have a factor of 2, and then factor of 2. So one is have one anti-homomorphic and homomorphic, the other is homomorphic. Okay, that you can get. And if you act the anti-homomorphic on here, you get this term. So that's how you obtain the here. So as you can see, so this is equal to 0. Therefore, this quantity has to be holomorphic. Okay. So in flat space, DZZ is holomorphic, as we saw in the free theory. In flat space, TZZ is we just replace like this way. Okay. But however, if you consider conformally flat metric here, there is a cost of this conformally flat metric. Okay. To connect between TZZ and holomorphic operator, there is a cost due to the non-flat metric. So therefore, this is in some sense, this is the source of this Y anomaly. In some sense. So therefore, so there is in flat space, this is the case, but in the non-trivial Riemann metric, so HAB, when HAB is not just usual metric or delta AB, then there is a difference between holomorphic operator and TZZ. That's the source of Y anomaly. And we like to determine what's how they are different by using conformal wide identity. So we can just use conformal wide identity. So now the conformal wide identity in not flat space. This is already, you can do the similar thing. 2 pi. So you just conform word identity on a non-trivial curved worksheet. So instead of the ordinary derivative, we have homomorphic derivative. No, sorry, not homomorphic, covariant derivative. z plus okay, so this is a current for plus. So you just you just replace the usual holomorphic derivative to covariant derivative to consider the general background, curved background. And you have an anti-holomorphic current. So this is just you can just take a look at the previous note. It's 3.11 currently. You just replace covariant derivative. Okay, so I significantly biased in this section 4, so you should take a look at the updated one. So this is the, sorry, I omit times operator. Okay. Times operator. And now we plug TZZ into here, and also the TZZ bar into here. And the anti-homomorphic part, you just replace anti-homomorphic part. Okay, now we can do that, and then we can just boils down the ordinary Cantor integral. I mean, what's nice about in 2D CFT, you can always boil down Cantor integral with OPE. Cantor integral. So oh my goodness, I already erased. So the plug this quantity and this quantity by using this one and that one. And then this is equal to the homomorphic derivative acts on TC. Essentially, this part will give you TC. As far as I remember. This is not the case. Oh, I'm sorry, I may be wrong. I already forgot. I already forgot the detail. Maybe it's better not to state anything. I think if I do the honest calculation, you will get this one. Yesterday I did that, I already forgot. And then partial E bar, C bar, Z bar. So this is the case. So TZ here is this quantity. Let me check my calculation yesterday, just in case. If I can answer immediately. Okay, maybe it's better not skip. What was that? Oh yeah. Anyway, I think I don't think I can reproduce now, so it's better to skip. Okay, so I think if you do an honest calculation, you will get this one. How do I do that? Oh yeah, it's written here. Sorry, so it's written here. TC, but this one is indeed the same as here, almost same as here. And you just replace this one by this quantity is replaced by this quantity. Yeah. So now I remember. And do this derivative, this one is the same as this part. This part, indeed. So you can replace this part, except up to this epsilon, you can replace TC. And it's the same as on the homomorphic part. Then, so this will give you the same transformation rule. So once you plug, so this is conform word identity, Takahashi identity on curved wordsheet. And the plug operator here, replace operator by TW, whatever. So therefore, delta epsilon T of T can be understood as the contour integral. I mean, I'm going to, I can omit the anti-homomorphic part. I just focus on and then homomorphic part. Okay. So this is the usual contour integral, and then one can take, oh my goodness, it should be W. W and W. I need a new choke, and then I should have brought a good choke here. So then, again, one can use OP of the holomorphic, this just ordinary Virasoro type symmetry, so one can just apply the usual OP of TPW is equal to usual C over 2 Z minus W squared. It's just holomorphic transformation for stress energy tensor. Plug into here for OPE. Then what you get, and do the contour integral. And what you obtain is delta epsilon of TZ is the same as a plug case. So that's what we have seen. So at the beginning of the lecture, okay, and are you guys following? Then another thing we can take a look at is this one. So this quantity from here so here we take variation with respect to this relation, so therefore delta epsilon TZ is just a delta epsilon TZZ bar, not TZZ, TZZ plus minus 2a delta E omega minus 2 del omega delta E omega. That's transformation rule coming from this definition, and we can compare both. And as you can easily see, they're very closely related, and under the certain relation, under the Fourier transformation, this is infinitesimal transformation. So now we just do the infinitesimal transformation like this way. Then under this one, stress energy tensor, energy momentum tensor, is just a transform on the ordinary way. Partial z, c tilde minus 2, z of z. Okay. The omega of z tilde is just a do the ordinary transformation for metric under the corner transformation, and plug this one into here, okay, by using this one. Then what you obtain, so this under this transformation, this is good exercise to do, and this is equal to, this is actually indeed complicated, but you can do that. Yesterday I did that, fully confused myself, and that you can do that. I mean, I plan to include the homework, but it's too many, so I just omit. I asked you to derive this one, but I think it's too many. But if you're interested, you can do that. Okay, so this is the, instead of ordinary calculation, you can just derive. Just plug that one into here, you get this relation. Okay. Any questions so far? So by comparing this one and this one can easily relate A is equal to, what was it? I realize. So trace anomaly, or it's called trace anomaly, or Y anomaly, is equal to minus C over 12 of R rated scale. So in curve background, there's a Y anomaly which is proportional to central charge. Proportional to central charge. So therefore, in order to avoid the Y anomaly, the total central charge has to be 0. However, what we learned is that the central charge is indeed d minus, let's see. So each boson, each direction mu runs for 1 to d will give you total. Each boson will give you central charge 1. So if d is equal to 26, the bosonic central charge is 26. So therefore, you cannot avoid the Y anomaly. So therefore, quantum mechanically, Y anomaly is broken. However, what we will see is that as I mentioned, so we will talk about the ghost. To fix the gauge, we need to introduce Popov ghost. And this ghost, it also has, ghost sector has also central charge. And this central charge, indeed, C ghost is equal to minus 26. This ghost central charge cancel with bosonic central charge, and they cancel each other. And at the end of the day, if the dimension is 26, okay, so in general, central charge is the same as the target space dimension, D. If the central target space dimension 26, it can cancel with ghost central charge. And at the end of the day, it's free from Y anomaly. So therefore, in order to avoid Y anomaly, the target space also has to be dimension 26. That also consistency condition. To have bosonic strings should be d is equal to 26. That's another condition. So this part I will talk about maybe next lecture. So let me move on. So this derivation is different from Polchinski. Polchinski derivation is a bit different. I prefer this derivation because, anyway, personally it's hard for me to read section 3 of a Polchinski, and then I just try to avoid the derivation of Polchinski. So next I will talk about so now we talk about curved worldsheet. Next we talk about curved No, it's the same. Is it different? I think I didn't print out my lecture note till BC Ghost. Isn't that the same? Okay, let me check now. Let's see. Polchinski's section 1, 2.5.11. Okay. Oh, but he only considered holomorphic sector, that's why. And he forget about the anti-holomorphic sector. So we can similarly consider, so I mean, he just start with the action S is equal to B. You can also add holomorphic sector, you need to add this one. So he just only focus on the holomorphic sector. Am I correct? I may be wrong. Let me check my lecture note. I may be wrong. I may take it back. I already forgot how it works in the BC Ghost. Let me check my lecture note. What did I say? Oh yeah, it seems like I only talk about holomorphic sector. Or not. Yeah, I think both anti-holomorphic, holomorphic sector I consider. Yeah. So if you look at my lecture notes, page 36 and 37, I just consider this action. And each sector will give you minus 13 and minus 13. And in total, you get 26. And here, even here, the C left is D over 2, and C right is equal to D over 2. And they counter with this one. Okay. So, yeah. So, yeah. So it's okay. Any other questions? So let me move on. So now, we just consider a curve worksheet to the flat space. That's from here we obtain the wall anomaly, and now we generate a bit more. Worksheet. Maybe it can be curved, whichever. Yeah, I mean curved. Yeah. Worksheet to general manifold M1, D minus 1. And it has non-trigonometric G mu nu. Here it should be eta mu nu. And again, we will see the action becomes so now, string sigma model action so action is indeed d squared x squared h HAB. So in the first lecture, what we saw is eta. So this is the first lecture. So now we need to replace the eta mu nu by G mu nu. Okay. G mu nu. Oops. So then, this is actually free scale. So as I mentioned, this is free period, free boson. But now here it's interacting. And it's called nonlinear sigma model. So interacting. And as you learn in the quantum field theory, so the scaling transformation, breaking down of scaling transformation at the quantum level is captured the beta function. So interacting theory, so what you learn is whatever QED or QCD, whatever. In the you have a coupling constant 1 over G on Mills square. Essential trace F mu nu, and then plus let's see, and plus yeah, maybe I should write down here. So what times G on Mills square and plus a Fermat. So this is QED or QCD you consider. And then here, classically this G is the dimensionless. But at quantum level, as you change the scale of energy, this G coupling constant, Yang-Mills coupling constant changes. Okay, that is captured by the beta function of G, which is d log E by whatever G Yang-Mills. G Yang-Mills that depends on energy scale. Anyway, that's so at the quantum level. Once you vary the energy scale, G can be different. G can vary. Okay. So therefore, if you include the loop corrections as you're learning, whatever. Anyway, so let's do the QED case. Like this way, if you consider the loop amplitude so one can consider the loop quantum correction, and if you consider quantum correction, you receive some. You will see the coupling constant depends on the scale of energy. So scaling of energy essentially roughly meaning, I mean, once you scale the space-time, once you zoom into the space-time, so you will see the different coupling constant, different way of interacting with photon or quark and gluon in QCD, or photon and electron. Okay, that's how they interact. So that's coupling constant measures. And then, so since we know that so now the matrix is non-trivial, and it's a not interacting theory, interact. So this coupling constant measure how the photon and electron interact, okay? This coupling constant, so this coupling constant show up this D slash. So this coupling constant measure how the gluon and the quark interact, okay? So now, interacting theory, so you need to be careful about the quantum effect. So that's what we need to do. And this scaling of this, depending on this energy scale on coupling constant really means that this, how this interaction depends on scaling of the scale, okay, space-time. So therefore, this beta function encodes the information about the Wow anomaly. So therefore, here I'll be very brief, and I will follow Green-Schwarz-Witten. Green-Schwarz-Witten section 3.4 yesterday. I just read Green-Schwarz-Witten. I mean, section 3 of Pociński, for me it's hard. So I just avoid the Pociński section 3 and I just follow the argument of Green-Schwarz-Witten. I'm not sure if I don't think I can finish today, but let me move on as much as I can. So now, yeah, I think there is some constant. I'm already omit some constant here. So we just, if you replace G mu nu, so to see how it gives you interaction theory, is that for instance, you can just take the perturbation around the flat metric, this A mu nu plus F mu nu x, then the partition function. So if you consider path integral, and do the perturbation around the flat metric here, you can just have first order. Actually, to write the first order, I think I should restore the constant. So the first order, if you do the perturbation, minus s naught 1 plus 1 over 4 pi alpha prime. Oh my goodness, I cannot write down. Oh, that's why the cost of writing big. Okay, so I just plug this one into here, and do the tail expansion of the e to the minus s. You just first leading order is 1 plus this one. Okay, I just do the tail expansion. And if you do the tail expansion, as you can easily see, this one is give you. So this part, as we already know, this part is the same as inserting. This part is inserting massless operator. So as we learned, so this alpha minus 1 acting on vacuum, the state operator's correspondence this way is essentially e to the ikx. Okay? So this part show up here, indeed. So this means that the perturbation, you need to insert lots of operators in the perturbation theory on the flat background. This is a the sign of this is you need to consider the interaction theory. And so therefore, we do some perturbation theory on this path integral. And this part, I'll be very brief. This one, if you try to do very, very careful, and you need to do lots of computation, quantum correction, and so on. So I'm going to be very brief. So, but in main message that the main message here is that the target is curved, then the theory is interacting. And the scaling, the theory depends on scaling. The scaling is measured the beta function of G mu nu. So beta function G mu nu has to be 0 to be consistent quantum theory. To avoid an anomaly, anomaly. So the main message. So to see this, to compute beta function of the graviton field, so we need to consider the following thing. Suppose we just do some perturbation theory, and then this I will be very brief, and then I just cite what is CT89. I just cited one reference for this part. I mean, even Green-Schwarz-Witten, it's very brief. Yeah, so this CT89 in the is a good reference for this beta function computation. But yeah, even Green-Schwarz-Witten is very brief. And to be honest, I cannot follow the argument to section 3 of the potency. So first, let's just perturb x sigma t is some constant times x sigma tau Taylor. So it's just from perturbation. So sigma tau is the of course coordinate of the worksheet. This is sigma tau, and you just map some just schematic. Being schematic M1, D minus 1 dimensional Riemannian or Lorentzian manifold, and the x sigma t sigma tau is the local coordinate of the target. And then you just pick a point here, and then you just have x naught. And suppose we just consider constant map. All the Riemann surface collapse to the point. So that's a simple max x naught, and you just do the bit of perturbation. That's what we are going to do. So then the metric perturbation G mu x around here, so this point x naught. So then we just look at only like a neighborhood around this x naught point is equal to G mu nu minus 1/3 R mu nu. This is just a standard Riemannian geometry x lambda rho plus order x cubed. So here, what we are doing is that as we learn in GR, so take a point x naught, and the curvature here is g mu nu, and if you deviate a little bit here, the curvature, so metric here, so g mu nu is a metric at the point x naught, and if you deviate at the point from the x naught, the metric is indeed deviation is captured by the curvature. How they are different is, takes the second derivative of the, if you do the Taylor expansion and the second derivative is captured by Riemann curvature, right? So that's how we show up the perturbation theory of this nonlinear sim model. So therefore, the action can be written as follows. S is equal to 1 over 4 pi alpha prime e squared x HA. So now I just take HAB is just a delta AB. Just simple simplification I made. And G mu nu minus 1/3 R mu nu lambda nu rho x lambda x sigma plus dot dot dot. Okay, so here you can just consider it's just constant. Now it's constant, but now so you have a interacting term. So this x times, the coordinate times Riemannian tensor times this part will give you interaction term. Okay? So therefore, the nonlinear sim model is interacting theory, and we just scale. So here, so if you scale x goes to 2 pi alpha prime x, then this can be written as the usual kinetic term but 2 pi alpha prime over 3 r mu lambda mu rho x lambda x rho plus dot dot dot. So now, so if you scale x to the square root 2 pi alpha prime, now so string coupling constant show up here. So this can be treated as an interaction term, okay? And we want to compute the beta function for this one. And that will give you how the theory depends on the scale. So, okay, so so in particular, so what I meant is so depending on the action on the scale can be treated as the following. So one is scaling transformation will give you the on one hand the scaling transformation will give you this square root h delta a h a b t a b, which is minus epsilon d squared. So this is usual scaling transformation will give you from action. On the other hand, we can have the beta this scaling of the theory can be understood as um, of the pressure law. Therefore, this scaling of wire anomaly can be captured by this beta. So this is essentially the beta function. So this part is beta function. On the metric, therefore, this beta function show up in the is wire anomaly. So now we are going to do the ordinary perturbation series. It's very roughly speaking. So now here we have the interaction term. I think I should erase here plus dot. So by using this, treating this one is interaction term, so we compute while invariance. Beta function. So x mu of x1, x mu of x2 is indeed, you can just have the free integral of 2 pi of square. This is just propagator. Okay, square e to the I k is just free integral. And then you have just the free level amplitude. And then you have a one loop correction coming from the loop integral times. So maybe I should write down plus 2 pi alpha over 3 r mu nu times p square p 2 pi square 1 over p square, and so on. So this one coming from loop integral. So we just consider essentially x mu and x nu, and then this propagator is just a leading term. It's a Fourier transform of this term, the leading term. But now we have x mu x rho, so that you can have some loop integral for here and around the p. Okay? And its coupling constant coming from this r mu nu lambda mu rho, and you just contract with metric g mu nu. Okay, that will give you this one. Yes, and if you use just I don't know why I just this time to be honest, I don't trust what I'm doing here. Have written word? Did I write? So somehow I have written some weird terms. This is just typo, and so on. So plus dot, and you can use. Unfortunately, I don't have time so much. Just ordinary regularization in field theory. 2 pi square 1 over p square is 1 over 2 pi log divergence. So you just have cutoff space and E. That will give you the correction to one loop correction to d g mu nu. And if you can compute, essentially, I don't have so much time, so I'm just going to be very brief, and I will recap next time a little bit. So this time we will give you beta function of G mu nu. So essentially, so this term will give you essentially, so roughly speaking, so if you go to the Fourier mode, if you go to the momentum space, this can be written, so therefore this one correction is essentially this one. To plug this one into here, up to some factor, I'm not careful again, mu nu, what you get is one loop determinant, one loop correction plus subreading correction. Subreading correction. And then if you take beta function is G mu nu is so partial log epsilon. So this is now new energies G correction G mu nu lambda epsilon and plug G mu nu lambda energy scale, and then here what you get is the alpha prime R mu nu. That's what you get. You have to be careful about the quotient. So I think if you compute subleading correction, like a correction very carefully, what this 1/3 will disappear, and then what you get this one. Okay. So unfortunately time is up. So I will recap next time. So in order for beta function to be zero, the target space has to be reached flat. Okay. So in order for the theory to be free from wild anomaly, the R mu nu one loop beta function has to be zero. So this is called reach flat. So the target space has to be reached flat in order for the theory to be well defined. And then, so at this moment, we just consider on the bosonic string. This also appears in the superstring, and the reach flatness condition will give you so-called Calabi-Yau 3 form, Calabi-Yau condition. So this one will give you Calabi-Yau manifold. The target space has to be Calabi-Yau manifold. Okay, so that's. I'm going to be very brief. I'm going to recap due to the time. So due to the time, I was very brief, but I will recap next time a little bit. And then move on to BRC quantization or ghost sector. Let's finish. So if you have questions, just tell me.